Welcome everybody. This is lecture 10 of CS267, and we're going to go over some of the advanced features of message passing interface and generally collective communication algorithms. In fact, I could have probably swapped this title because we're going to start with collective communication. And just as a recap, the last lectures, we reviewed the distributed memory machines and their programming at a high level. We described some of the topologies that are used, and we got into MPI. What is MPI? What can you do with it at the high level? And gave some examples with point-to-point communication. And the collective algorithms are probably one of the ways that makes programming distributed memory machines more productive and arguably higher performance in the situations where you can take advantage of it. I'm going to go over what I really mean with collective communications. But before that, I want to maybe use one motivating slide. This has been catching on in the last 5 years, where the deep learning community has discovered the importance and performance benefits of collective communication and has been building their own libraries that does that. So here you see the set of communication backends that are supported by Torch Distributed, arguably the most popular package for doing deep learning on a distributed memory architecture. And you can see that MPI is supported, and nicely MPI supports, of course, all of these because it's been around for more than a quarter century at this point. But companies have been developing their own, like Glue is Facebook's collective communications library with a long name. Nickel is arguably more popular, NVIDIA collective communications library. This capability check marks might be a little, by 1 year, outdated. I think Nickel now has send and receive support, but you can already see that the focus is not actually in send and receives. The focus has always been in collectives. And the names of these alternative libraries are the collective name is ingrained in them. And you can argue why they do it, and there are multiple reasons why they do their own, then going through MPI. And a few of them I will explain while I talk about the algorithms. But at a high level, one of the reasons is the MPI is, I forgot how many pages it is. There's a lot of requirements and a lot of things that needs to be implemented for a library to call itself a compliant MPI implementation. And a lot of companies might not be willing to do that. Instead, you can just say, all I need is these 5 operations to make my tasks fast. So I'm just going to implement them separately. And that's one reason. And there's also a semantic mismatch from some of these applications with MPI in certain cases, which I will again describe. So what is collective data movement? It's really multiple processes collectively participating in a communication task. Is one way to describe it. And this can be a broadcast where one root processor will broadcast a value to all the other processes. And I intentionally use the word process as opposed to processor because you can map MPI processes to hardware resources in many different ways. You can say, I'm going to assign one process to a single node, or I'm going to assign one process to a core, or I'm going to assign one process to a thread, and various things in between. You can say each NUMA domain. So I'm going to use the word process to describe the abstraction. That doesn't refer to the architecture. Scatter and gather are inverses of each other, where I think a scatter means there's a root process and it has ideally P pieces of data, and it scatters to P processors. And the gather is the inverse of that. So all of these in collectives, there is a concept of a communicator. You have seen that MPI by default describes a communicator called MPI convert, and we have used that in an example before. That includes all the processes that are participating in this MPI run. But you can define subsets of those in some almost arbitrarily. and create different communicators from that. And whenever you're doing a collective communication on a communicator, all of the processes in that communicator needs to call that function. Otherwise, your program will likely hang, right? And then for broadcast, there was a single root processor. But for some of these operations, and as well as gather and scatter, but there's slightly higher level versions of these collectives that all are prefixed with all. And in this case, all processes collectively become the senders, as opposed to one root process being the sender or the receiver. So in all gather, everybody has a piece of data. And in the end, you expect every process to have a copy of the aggregate data from all other processes, including its own, to start with. And no operation has been done here. They just concatenated in some particular order that are given by the ranks of the processes. And all to all, arguably the most general primitive, where every process has some data that it needs to send to every other process. And these are individualized, meaning each process has a different set of data to be sent to other processes. So this has been called in the community as personalized broadcast, personalized all-to-all broadcast. And there's different names if you want to figure out the algorithms. While it's very general, it's also hard to come up with really good algorithms that are better than just doing point-to-point communication with non-blocking point-to-point operations. And we've seen non-blocking I send, I receive, at least briefly in the previous lectures. So there is also a couple of operations which not only just gather the data without doing an operation or scatter or broadcast. These ones in the slide, reduce and scan, and variants of them, including all reduce, do actually perform some sort of computation while also doing the collective communication. Reduction in particular does either sum, take the min, take the max, or perform some sort of operation on all these data in aggregate from each processor. And reduce is, since it's not prefixed with all, the whole data goes to a root processor. And so you have to describe which processor is the root and where all this data will be reduced to. Scan is something you have seen in data parallel lecture by Kathy from last week, I believe. It's a prefix sum. There's a different name for prefix sum, where you basically get I don't know if there's a better word than the prefix sum. The first element goes to first process. The first operated with the second element goes to the second process. The first three goes operated together with whatever operator that you pass goes to the third processor, and so on. So in general, this is really at each process, it's all the way up at the process I, all the elements AI to A0 backwards are summed up or reduced and stored in that process. And that comes handy in a lot of operations. So as I think this is stuff that I already said, all versions deliver results to all participating processes, not just root, but there's very convenient versions of these that are all suffixed with we. And the we here describes that these entries of each element in the processors can be of different length. And let me describe it an example. When we're doing gather, the default gather operation means every process has a fixed size of data, and that can be like 1 or 10, but it doesn't actually admit different lengths of data from different processes together. For that, you will need gather. It's just syntactic difference. It has a longer signature that you have to pass an array of lengths that are from each source processor that are supplying the data. but that's all about it. And some of the optimizations in the algorithms become harder due to variable lengths. But that comes with the convenience. And as I said, the reductions and scans or reduced scatter-like operations need to take some sort of combiner function. This can be either a built-in one or a user-defined one. I think I'm going to skip this slide, but I'll go through an example of an algorithm that Jim is actually going to talk about again in, I guess, next week or so in dense neural algebra class. I found it pedagogically useful to describe it and use it as an example to explain collective communication, and especially on subcommunicators, because I've been talking about the reality that you can communicate on subsets of processes as opposed to just communicating on MPI COM world. But I haven't talked about how to do that, and this is a good time to use it. SUMA is a dense matrix multiplication algorithm that is commonly used in various parallel BLAS-like implementations. And this is based on block order products. It's a two-dimensional algorithm I will describe. Suppose you have logically organized your processors, or processes, to be more exact, in a two-dimensional process grid. And here I'm going to simplify the case where the process grid is 4 by 4, meaning a perfect square number of processes you have. And the big matrix itself is divided into 16 little pieces, as you can see. And at every stage, the algorithm broadcasts a panel, k columns of the first matrix and k rows of the B matrix. And all the recipients of this data that are broadcasted from the active panel will do an outer product of the little piece of broadcasted data they receive, this red subcolumn, as well as the little piece of the subrow, the blue subrow, and do an dense matrix multiply in this tall, skinny, and fat, short matrix and update its own data. So it's an owner computes algorithm. Whomever owns Cij will do the computation and update Cij itself. And you can see that you can choose k pretty much all the way from 1 till the whole length of the n divided by square root of p. You can broadcast the whole matrix if you have enough memory to store 2 copies. And that's what we're going to do in this example because it's much easier to describe. But one of the strengths of this algorithm is the ability to choose k arbitrarily so that it can handle cases where the process grid is not perfect square or the matrices are not as well also square. So that kind of helps you choose a k that will make the programming much easier. But we're going to go over an example where k equals n over square root of p so that each block is broadcasted only once. But what you see here is the broadcasts are happening in groups, meaning the AIK piece, ALK piece actually, I think, our IK piece is owned by the processor here. What is it? Let's index it with 0, 0, 1, 2. 2 by 0 process, and it will only broadcast it along its process row, meaning to the process right next to it, and next to it, and next to it. And it's not going to communicate with any other process for the broadcast of his piece of A. The other processes will receive pieces of A from a different source processor. And in this case, you can see this would be P10 here. We'll send it along its process row too. So simultaneously, everybody will be communicating with its neighbors along the process row. And the same thing is going to happen for the B matrix, except that that communication will happen along the process column. So whomever owns this first piece of blue sub row will send it along the process column down. And this is depicted in the picture for the last column. Now you might as well ask, okay, how do we do that, right? How can I start with MPI convert and get subcommunicators that describe only the processes in my process row and only the processes in my process column? Well, MPI knows that this is a common case and has a particular function that allows you to do that. It's called MPI comp split. So you're given an existing communicator, which if you're starting from scratch, it can be MPI convert, or if you are already inside a library, it's whatever that library's concept of word. And you basically give a color. You say this is a collective communication call. Sorry, it's a collective call, meaning every process that is in the source communicator has to call the split at the same time. And so for our example, all 16 processes will call split, and they're going to supply a color. So if I'm trying to group them into 4, and each group includes one process row, all the processes in the first row needs to be given the same color, let's say yellow. And all the processes in the second row needs to be given the next color, let's say green. And the algorithm will basically create new groups and attach context to create new communicators for all the processes that have the same color. And then the next question becomes, well, how is it going to rank them? Because in each communicator, each process has a distinct rank. And this is always ranked from 0 to the communicator size -1. Makes programming much easier. And it's going to use the key to rank them. So the keys needs to be unique, of course, but this is somewhat easy because you already start with unique ranks. You can pass the ranks, and it will basically sort them and renumber them from 0 to communicator size -1. It's all nice and abstract, but you'll see in the code, at least in the pseudocode, that it's actually fairly easy to use. So let's come back to Summa algorithm. And here what we have is a high-level description of the algorithm we have already described in verbally, and using the picture 2 slides ago. For all the inner products, this is the outer loop, k from 0 to n-1, or n over b. In our case, we're going to choose this to be pretty high, so it's going to only iterate to square root of n. And all the processes in parallel will broadcast along the process row for A, and all the processes owning B will broadcast along the process column. And this is going to end after n over b -1, n over b iterations. In our case, since B will be large as the whole local matrix, this is going to finish in square root of p iterations. So for that description, here is what it will look like. No guarantees that this would compile, but it's pretty close. Let's say we're given, we already are operating an MPI convert land. We can create our row colors by dividing our rank with square root of p. Let's say for generality, I use the processes along the column dimension, but think of it as square root of p. What would this do is everybody in the first row will get color 0. Everybody in the second row will get color 1. So this is exactly what we want, because when we call split, then the first row will become its own communicator, and second row will become its own communicator, and so on. Now we have to do this for the column dimension, and for that we can use the modulus. If I do this, divide my top level rank, meaning my rank in the communicator, original communicator word, with PC, choose the modulo, all the processes in the first column will get the 0th rank. All the processes in the second column will get the first rank. Sorry for 0 indexing confusion here, but you get the point, I hope. And you can just pass the original ranks as the keys because they're ordered in the right way. And all that MPI comp split will do is just renumber them, as I said in the previous slides. So, okay, now we got our row and column communicators. How can we execute our algorithm? Now we go from K0 to PC because we're going to broadcast the whole local matrix along the process row and column. If we are the broadcasting processor, meaning our row color is K, our column color is K, we basically copy our local matrix into the data that we're going to broadcast, which is ATEMP. And then we call broadcast. Now everybody's calling broadcast, but only the root, which is K, has a valid copy. It got a MA copied into ATEMP. Everybody else is effectively junk in ATEMP. And somewhere in there, I didn't put it in this code, is, well, ATEMP is somehow initialized. That's not in the code, but you have to do it, of course. It needs to have enough memory for, of course, for me to be able to do memcopy, and also for the broadcast to work in the recipient side, there needs to be enough memory. And do broadcast, that means everybody's ATEMP and everybody's DTEMP now has the data once the broadcasts are over. And the good news with broadcast with this way is it's blocking. By the time it returns, everybody has completed this communication. And now I can call some sort of simple DGEM with the A and B as inputs and my C as my output. I have to capitalize this C clearly. Or maybe not, the input doesn't capitalize. So what do I see here? That's about it. And that's all you need to do to implement a very naive summa algorithm that executes in square root of p stages. And as long as the matrix is large and you have enough memory, it might actually perform okay. Now, let's continue on our collectives. We have said that some collectives allow you to perform certain operations on the data during the communication. And these were reduce, scatter, all reduce, scan, and various versions of scan. And there's, I think, exclusive scan, and might be another one. So what are those? The built-in ones are listed in the slide. And they do pretty obvious things like finding maximum, minimum, computing product, sums, and if the inputs are logical, they will do logical ands and ors. And they actually do some more convenient things, like it will find the location of the maximum element, which can come handy in certain operations. There is some semantics you might want to know that if the operation that's given is not commutative, then the reduction MPI implementation performs the reduction in the canonical order. But if it is commutative, it can do practically any order. The spec kind of leaves the bracketing, the associativity vague, and says that the same bracketing for all elements are not strictly required, but should be strived for. Now, it's, I guess, in the eye of the reader to interpret this thing. So you can't really trust that the implementation will do the right thing if you don't have an associative operation. What are the costs of these collectives? So here's a table for lower bounds from the papers that are cited at the bottom. These basically are communication costs on one process. And usually that's the process that has to do the most communication. In some operations, everybody does the same amount of communication, but in some others, there is one process that is clearly doing more communication than the others. And that's basically the maximum on that process. So what does that mean? Let's look at all gather. In all gather, I am giving an input. Each piece is n over p. So this slide is a little underspecified, and you have to read beyond the table. For example, what is the input size, right? For all gather, each process is expected to have n over p data. And that is, at the end, everybody has n data. That might not be always that case. So read the text that refers to the table. And obviously, some of these almost all of these lower bounds are trivial if you think about them. The bandwidth especially is fairly obvious as someone who's doing all gather and starts with n over p data and has to end with n data. I have to receive p minus 1 divided p times n data. And there doesn't seem to be any way to get around that. And so that's why these lower bounds are fairly obvious lower bounds. It strikes me positively, surprisingly, that these lower bounds are to a large degree attainable. So you'll see some algorithms. Let's continue focusing on all gather. Remember, all gather was everybody has a piece of distinct data, and at the end of the computation, we want every process to include everybody else's data as well. So everybody will have the same identical aggregate data. You can start with the simple algorithm that's called the ring algorithm. At time t, you just basically send the data you received in the previous time step to your right and receive new data from your left. And assume that all the processes are connected to some sort of ring, even if that's not the case in reality. So I'm not implying any hardware connectivity here. I'm just given P processes, and I have no information about how they're connected in the network, but I know I can send messages and receive messages among any pair of them. I just don't know how fast that's going to be. So it's likely that the underlying network is not a torus. And when I'm sending data to my left, or sorry, receiving data from my left, it might go through multiple hops, but that's not a problem, at least in this algorithm implementation. It's a problem potentially for performance. And at the 0th time, I only send my original data because I haven't received anything yet. So what's going to happen is after p minus 1 steps, everybody will have all the data. And at any stage, I am sending n over p data. And there are p minus 1 stages. So n over p times p minus 1 is the bandwidth cost. And every process will spend the same amount of bandwidth, sending and receiving. So this is actually optimal bandwidth, as you can see from the lower bound, and which is obvious, right? But it has a high latency, meaning if 10,000 processes are participating, it takes a long time for this data to go everywhere. It might sound a really bad idea, but here is the caveat. It's actually used extensively in one of the highest performing collective libraries, NVIDIA's Nickel, for every single collective operation, not just for all gather, but also for broadcasts and reductions. Everything is implemented in a ring algorithm. And the reason for that is twofold. One is it's not the whole data you're sending in Nickel's case. And frankly, MPI doesn't have to send the whole data either. You can pipeline this, meaning when the algorithm starts, you can start sending a relatively small piece of data. And while it's moving to its target, you can start the next one. So you kind of fill this ring in the optimal way. You're not getting around the p minus 1 bottleneck, but for certain sizes, especially if your data is large enough that you can fill the pipeline efficiently, those p latency becomes almost unnoticeable. And we'll see an example, an actual example that's been measured. This might look like a more catastrophic problem in broadcasts, because in all gather, everybody's sending data. So everybody is somewhat busy. How about broadcast? If I was starting a broadcast from the source on the top left, and the data started moving with the ring algorithm, well, at the first stage, only this first link would be used. And every other link and every other processor would just be waiting. At the second stage, only the second link would be used, and everybody would be waiting. That looks like a horrible idea in terms of link utilization. If I was doing broadcasts, again, in all gather, I don't have this issue. But even in broadcast, the ring algorithm is not catastrophic due to pipelining. Instead of just using one link at a time, I would divide my data into 100 pieces and send the first piece to my neighbors. And in the second stage, my neighbor sends that data that I just sent to his neighbor while I do the second of my 100 pieces. And as you can see that after P minus steps, the whole pipeline is full and I am at full utilization of all the links. Of course, there is the initial filling the pipeline problem, but that's also in practice not a real problem in nickel semantics. MPI collectives are blocking, meaning everybody needs to arrive to the collective for it to start, and everybody leaves the collective at the same time. So there's an implicit barrier, semantically speaking. In nickel, that's not the case. It's not asynchronous like MPI, asynchronous definition, but it's not blocking either. So as soon as I am done sending all my 100 pieces, even though there's still data in the pipeline that needs to go its destination, since I'm done with my share in the broadcast case, I can exit the collective and continue doing my next step of communication or my next step of computation. And if I got into the next broadcast faster than the rest of my peers, I don't need to wait for them because I exited first. It's likely that I'm going to arrive to the next communication also earlier than my peers. And I can just start my next ring algorithm there. So this way you can see that you don't even need to fill the pipeline for each operation. You just need to fill the pipeline once for a program, and the across collective calls, the same pipeline will be retained in some sense. But that's too much of a parenthesis for nickel that I don't actually describe in the slides at the moment. So let's come back to our altogether and more sophisticated algorithms. There's obviously a better way to do that for this case. It's called the recursive doubling algorithm. And it's fairly simple. At time t, each process, let's say process I, sends and receives all of its current data. And what that means is all of its original data that it started with, plus anything that it received so far. Of course, in the initial step, there is nothing that it received. It's just going to exchange with a process that is 2t away from it. And at time t, t starts with 0, so 2t means 1, so it just does it with its immediate neighbor. And at the next step, it does exchange data with a processor that is 2 hops away, and so on. So that's great. And how many steps this is going to take? This is going to take a logarithmic number of steps, naturally. And the data exchange at each step will double at each step. And you can write down how much data is communicated per process by summing this up. And it's going to give you a geometric series with the base n over p, because it's n over p plus 2 times n over p plus 4 times n over p. So the geometric series with base a, and it's going to end after log p steps. So you write this down and you'll get this equation, which is n times p minus 1 over p. So the bandwidth is optimal. However, it's a little tricky for the non-power of 2. What if I have 40 processes and I have, I'll have to find the lowest power of 2 that is larger than 40, at least larger than or equal to 40, which would be 64. And I would run it on a grid like that and effectively exchanging empty data for some of those stages. That's not too bad, but you'll get something that kind of looks like 2 times floor of log p. Can we do better? It turns out we can. This is called the Buluc algorithm, and the Buluc algorithm is actually, there is a set of algorithms, a beautiful paper from I forgot the first name of the author. Is I think somewhere in Los Angeles right now, and likely no longer working in parallel computing, but it includes collective communication algorithms for a lot of different primitives. And this one is for the all-gather one. Here, it's like awfully similar to recursive doubling, but the differences are you don't actually go all the way to the last step. Instead, your regular exchanges will finish after the floor of log p steps. And what that means is, and you're not really doing, in some sense, recursive doubling. You're exchanging data with a different processor, and it wraps around. So what looking at the example, at first I'm just doing it with my peers on the right, and I'm receiving from the left. So it's not a send receive. I'm receiving and sending to a different processor. In recursive doubling, I was send and receiving to the same peer. Here it's different. As process one, for example, sends this data to left and receives this data from its right. And in the next stage, it's going to receive data from two hop neighbors, 3, 4, and it's going to write it over here, right? And at which stage the regular communication step is done. And just to remind you what the wrapping part is, processor 1 in the stage basically sent data to processor 5 because it's modulo p, it's two hop neighbor on the left. So it went over here. And after that, and the last step, there is an irregular step of only the remaining pieces are sent. That's great. The data is not ordered, unfortunately, but the data needs to be ordered for this to be correct. Good news, there is no communication for that, just the process can locally order this, right? There's a local shift, and it's not a sort, it's just a shift, so it's much cheaper. And once you do that, you get an awfully similar bound. And you might wonder why, if this is worthwhile. Now think of it this way. This will give you a bound that is ceiling of log p, whereas recursive doubling gave you 2 times floor of log p. If latency is really what you care about, just take processors 40, and you'll see that one of them gives you 6, and the other one gives you 10. So I suppose it's almost, sometimes it's close to a factor of 2 better, sometimes it's identical. And you'll see it in the experimental results. You compare recursive doubling with the Buluc algorithm that when it's a power of 2, they're awfully similar, right? They kind of hit the same mark. When it's not a power of 2, the Buluc algorithm is noticeably faster, right? So, and that's this regular typical curve. And similar ideas are used in other collectives. So this is not really special to all gathers, all reduce that is heavily used in deep learning, broadcast. They all have variants of these. The name is no longer recursive doubling if you're doing a reduction. In fact, it's called recursive halving, I think, naturally. And you can read all of those in this beautiful paper cited at the bottom. And on the right, you see something that I actually meant to say when I was describing the ring algorithm, meaning that that latency term actually doesn't show up as the message size gets larger for various reasons. And you see that for small message size, you might argue that this would have been slow, but 1 megabyte is not small enough. So for any reasonable large message size, ring algorithm is actually not that bad because it utilizes the network fairly well. All right, any questions so far? This has been one of the fewest questions lectures, or I'm just not seeing it? No.
I'll ask a question, Aydin.
Yes.
So why does Nickel use ring exclusively for all gather if there are better algorithms?
I mean, whether they're better or not is, as you can see, they're not all that better, right? For anything large enough size, the pipelining hides the latency. Now, it is entirely possible that when people push the boundaries and try to do collective communication in tens of thousands of processes at the same time, this will become a significant bottleneck. But for P in the ranges that nickel is currently optimizing itself, this doesn't seem to be an issue. And I think the other reason I explained is there is this semantic difference from MPI. MPI assumes that when you get an MPI collective, everybody arrives at the same time, everybody leaves at the same time. So it leaves no opportunities for pipelining across operations. Whereas nickel doesn't enforce that. So if process I is finished sending and participating in generally in that collective, it can just move on to the next function. And that allows you to pipeline across the whole program. And that takes away one of the major downsides of the ring algorithm, where you just wait for the pipeline to fill for many operations. Again, maybe this example is not the perfect one to highlight because it seems like the pipeline is already full for all gather, but that's not the case for broadcast, for example. Does that answer the question?
Yeah, I mean, my personal experience is the same, that ring has always outperformed all the other algorithms.
I think for long enough messages and the concurrencies people use, that's going to be the case. There is an MPI, just to say, doesn't mean that MPI actually by default uses any of the other algorithms. MPI has all these thresholds that are built in, and you can query them on query if you like, to figure out at what point it switches from X algorithm to Y algorithm. Now, good luck finding that environmental variable's name, but once you find it, you can query it. You can even change it if you care. You can say that as soon as the message becomes this long, start using this algorithm. There is all these things that are, in some sense, auto-tuned when the library is installed on query based on benchmarking. And if you believe that that threshold is wrong, you can even manually change it. So it's trying to do the best possible given the message size and the concurrency. Good to know. Here is synchronization. If you want explicit synchronization of processes, you can call barrier. The argument here is that you almost never need it because all collectives, blocking collectives synchronize, and there is usually some other thing that does this. Now, it is useful for performance benchmarking. You want to know how fast that communication was going to take and what is the, for example, load balance up until that point. You would have to use barriers to individually time the entry points. But other than debugging and performance, you probably don't need it. Non-blocking. So just like there is non-blocking I-sends and I-receives, MPI3 included non-blocking collectives, and they all are preceded with I for immediate, meaning immediately return the function, despite not having completed the broadcast, and yet alone start. There is no guarantee that MPI will even start broadcasting just because you called it. It has to do the operation when you call wait on it, but just because you called MPI broadcast, there is no enforcement of starting the broadcast. Some implementations might start doing it. Some implementations will just completely delay it until you call wait. So it depends on the quality of the implementation. And various other things that you need to know about. Perhaps the most important is, unlike blocking collectives, you cannot touch the buffers, send or receive buffers. Because until you call the wait and wait has returned, signal incompletion. There's always semantic advantages of using this thing. This allows you to do your own software pipelining, which is, we're going to do it for the Summa example in the next couple of slides for the same problem that we described. It potentially lets you overlap communication and computation. And again, another thing that we're going to utilize, both pipelining and overlapping. And finally, it gives some sort of noise resiliency. And this is best described as 5 people trying to hike, right? If 5 people trying to hike, and if you synchronously wait at any time somebody needs to go to the bathroom, then you're slowed down by the sum of bathroom breaks. But if all you want is to go from point A to point B, then you just let the person who's needs to go to the bathroom go to the bathroom. The rest of the group continues, and this will happen to every one of those, assuming everybody goes to the bathroom once. And in the end, you're only gonna stop for 1 bathroom break. And that's the same thing that happens when there is a noise at operating system level, and that will likely happen in process 1 and then process 4 later. So it's going to wash out if you don't enforce synchronization at each call. That's the potential benefit. Okay, come back to Suma. We don't need to go over the same pictures, but let's see how we can modify the code, the implementation to allow overlapping of communication with computation. In our example, recall that each process was sending all of its data to its process row and column. All the active processes that are responsible for sending was sending all of it. We can't really do efficient pipelining that way because the granularity is too large, but we can do something very simple. We can divide our local matrices into 2 pieces. And this is, of course, not going to give you all that much overlapping, but you can split it into 100 pieces technically. And I'm just going to describe the split into 2 case to describe a little bit of overlap. And if you increase that split count, you'll get your overlapping ratio will increase dramatically. Meaning if you split it into S pieces, you should potentially be able to overlap S-1 divided by S of the communication. And for S large S, it approaches all of the communication. So, okay, how is that going to happen? First, I am creating these requests objects that I have to keep track of the handles that are returned from iBroadcasts so that I can later wait on them. And let's create these objects. One is request 1, the other one is request 2. And these are for respectively the communication that happened at time I and the communication that is happening in time step I+1. And I will swap them out. So I will always have 2 sets of requests that are floating around at any given time. And request as an array of size 2 for the 0th element is for matrix A, and the first element is for matrix B. So I remember I started in this slide before I do anything within a loop. I am initiating the broadcast calls, and now I'm hoping the MPI implementation will start communicating them. And for certain high performance implementation, that might very well be the case. And now I go inside this loop where I start the communication of the second piece of my matrix. That's nice. And I will post those broadcast functions. Now, normally I have to go into the multiplication of the first pieces of data that I broadcasted right outside the loop. But I don't know if they finished. So I have to make sure that they will all finish. So I call MPI wait all with the requests of the ith iteration, the previous one that's outside the loop. And once the wait all returns, that means the broadcasts that I have initiated in the previous slide has completed. And now I can call my DGEM on that data because I know the data is full. So what is happening here? At this point, if all goes well, and MPI is making progress, it's a quality implementation, I am computing a DGEM, an expensive function, while in the background, the iBroadcast is happening for the next multiplication that I'm going to do. And that's the premise. And obviously, within that loop, now, since the first one is finished, next time I'm going to call broadcast for the first set of requests. And while I'm waiting for and then I'm going to wait for this once at the beginning of the loop, do the DJAM. You can see how this is all moving. At any point I'm doing DJAMs, there is communication in flight, ideally. And I actually misspoke when I said this is not going to overlap much. This is actually going to overlap pretty good. The formula is much better than what I thought. If you divide it into S pieces locally, you should be able to overlap an overwhelming majority of the computation, which is 2 times square root of p minus 1 divided by 2 times square root of p. For a large p, that's approximating 1. So, because again, even though I split it into 2, let's say I have a 4x4 grid, I have total of 8 stages, and 7 of which I'm going to be able to overlap. And for p equals 100, I'm going to overlap 95% and so on. And that's, I have to, of course, clean up and do the last DJAMs outside the loop, but this should be more or less correct. So this will likely give you better performance if your MPI implementation cooperates. Let me see what else is in the chat.
Oh no, I just posted a few reference to the papers.
Thank you, Julia. Well, that concludes the collective communication part. And now we're going to go to threads. And this is important because a lot of programming these days on clusters are done by some combination of a multi-threading library and MPI. Now there's different proponents, people that support using OpenMP or pthreads, or there's a group of people that will actually suggest we use MPI. But OpenMP is potentially the most popular one within a node. And so MPI process will be assigned to a compute node. And for all 68 threads, OpenMP will be running. Now, there's downsides of this approach, but it's very popular. And there is this top level, actually. There is actually a different one that's been emerging, and you can also try that, which is called MPI plus MPI. What that means is you internally also use MPI instead of these threading libraries, but we're not going to touch that. So we're mostly going to focus on using an explicit threading library that does share all of its data. MPI, remember, by default doesn't share data. And it really looks like this. There's multiple threads running within each MPI process. And now the semantics become a little complicated because multiple threads will be executing simultaneously. The fundamental questions is how many of them are allowed to communicate? And then you can say, where are they allowed to communicate simultaneously? Or are they just going to be ordered in some way? Well, MPI thought about this and has different support levels. MPI thread single means the MPI implementation does not want you to use threading at all. And that's increasingly rare. Almost every MPI implementation supports some sort of threading. And the most basic one of those thread supports are funneled, meaning there is a thread 0, the master thread, the one that called the MPI init. By the way, there's a separate function called MPI init thread. So you can't really technically run a multi-threaded MPI code by calling MPI init. You have to call MPI init thread. Surprisingly, this is not the case, and it's still going to be fine for funneled cases. But don't do it, and follow the spec, please. And the serialized means not only the main thread, but some other thread can also make MPI calls, as long as only one thread calls MPI at any given point. And the ordering is enforced by the programmer somehow, that there is no chance that two threads will make MPI calls at the same time, and that's called serialized. And multiple means multiple MPI processes can make MPI calls simultaneously. And of course, that doesn't mean happens before relationships are going to be automatically resolved. There's no way to do that. You'll have to still take care of certain data access issues, and we're going to describe them. And these are all inclusive in some sense. If I am supporting MPI threads serialized, of course I'm supporting MPI threads funneled by definition. Simple stuff, the MPI init, we know finalized without threads. How can I do funneled? Well, I can just say, I can ask for funnel support in my MPI init thread call. And if MPI doesn't give it that support to me, I can abort. And now I have this MPI, the OMP parallel loop, but it's not doing any communication. It's only doing computation. And once it's over, that I do MPI stuff. Remember, OpenMP will open up a parallel region, and it's going to close that parallel region. So at this point, when I'm in the do MPI stuff commented line, there's only one thread alive. So that's fine. How about serialize? Well, you can use it within that parallel loop, except you have to ensure that only one MPI process will call it at any given time. One way to do it is put a critical statement. Now, I'm not endorsing this as the performance optimal way of programming, but this is an example on how you can take advantage of the serialized support. And for the multiple case, well, basically you can do MPI stuff within the OMP parallel region without enforcing critical regions or serialization. I think it turns out that MPI doesn't require any implementation to support anything beyond single. But even though most most implementations will not admit this, they all, to my experience, support MPI thread funneled. Even if they deny it, I haven't seen a program crash. So the hard part of this understanding the logic really comes into MPI thread multiple, because for MPI thread funneled and MPI thread serialized, the semantics are fairly straightforward. And it's hard to create data races from the programmer perspective. However, MPI thread multiple is a little more complicated. When multiple threads, of course, make MPI calls concurrently, you don't know the outcome unless there is some explicit synchronization that is being enforced in the OpenMP level. That's because when you run that OpenMP code, it could have reordered these operations depending on how the cores are getting out of sync, how the OMP runtime schedules them, right? And so this sentence doesn't say anything special for MPI. It just says standard semantics of OpenMP. You can replace MPI with when multiple threads call library A, the outcome would be as if the call is executed sequentially in some, but any order it can happen. And this is nothing special to MPI going on. However, the ordering will be maintained within each thread, which is good, which is also not special to MPI. If you call function 1, then function 2 within a single thread, then that order will be maintained. And blocking. The blocking of MPI calls, like all sends and receives and broadcasts that are not preceded with I, will block only the calling thread and will not create an issue in the simultaneous running alternative thread. Let's get with real examples. So here's thread 1 and thread 2, 2 threads, 2 processes. Each process has 2 threads. And they're doing send and receives, except that in process 0, thread 1 is receiving and thread 2 is sending. And in process 1, the opposite is happening. No, the same is happening, in fact. So, and they're exchanging data across processes. this is a correct code and it has to execute correctly. And it should not deadlock because the blocking of, even though MPI receive and MPI send are blocking calls, they are not supposed to block the other thread. So when process 0 posts the receive in thread 1, it should be able to get the data from process 1's thread 2 just fine. So this should correctly execute, even though it looks a little contrived example. This doesn't have to correctly execute. And why? Because in collectives, it turns out the barriers can match the broadcasts. And that's, again, a little bit contrived example. But to illustrate what's actually going on is they can execute in any order, right? There's no guarantee that thread 1 and thread 2 will be ordered within processes. So their order might be swapped in process 0 versus process 1, in which case the barrier on process 1 will match with the broadcast in process 0. And that's a problem. And why does this not happen in the send receive? Well, because these don't match, right? Two sends don't match. The send only matches the receive. So there's no risk of that. This is the problem, okay. And of course you can, this is a more obvious example. This has nothing to do with communication. You have an object called the communicator, and there is a different thread that is freeing that object. Well, unless you enforce that by the time the free is called, thread 1 finished what it's doing with that communicator, it can totally segfault. And this has nothing to do with MPI. All right. So all the things that I said are included in this slide, meaning pretty much all implementations technically, in practice, sorry, support MPI thread funneled, even if they don't admit it. Many implementations now support MPI thread multiple. This was not the case when I was a grad student. And it was really hard to find an implementation that actually supported this. Nowadays, it's all over. It took a while because you have to do fine-grained locking to ensure correctness. And the libraries took a while to get there. The last line is actually fairly important. Watch out for Amdahl's law. Because you can write a lot of code with the funneled or serialized, where only one process is doing communication. But remember, in OpenMP, what ends up happening is you create a parallel region. You do compute, you close the parallel region, you do communicate, and there is a cost associated with that due to all these serialized regions. And in many cases, a network is not fully utilized when there is only one thread is communicating. And it's oversubscribed when everybody's communicating. So you can handle this thing several different ways. One is assigning multiple MPI processes per node. Let's say you have 68 cores of core KNL. You can say, I'm going to have 4 MPI processes per node, and each one of them will have 17 threads, something like that. And figure out what is the best number. Or you can use MPI thread multiple, but control how many are communicating at the same time. And those are potential ways of handling that. For really high performance bleeding edge computations, there is an alternative way is to keep all the threads alive at all the time. But that's kind of going against the OpenMP philosophy. But it avoids this Amdahl's law bottlenecks. Any questions so far? I have figured out that I can move faster when I'm not in the classroom. So for the first time since I put together these slides, I am making it to this last part of the talk with more than 10 minutes to spare. So one-sided communication. The idea of one-sided communication will be thoroughly explained by Kathy in the PGAS class. I think it's next Monday, partition global address this, but MPI supports it too. So I'm going to describe how to do it in MPI way. One-sided communication simply means you can communicate with another processor's data, at least another process, without involving the other CPU, and that's one. And the goal here is in MPI two-sided, data movement and synchronization are ingrained, and they're all integrated to each other. When you're communicating, you're also automatically synchronizing. But that doesn't always have to be the case, right? I want the data from the other processor, but I don't need the other processor to synchronize with me. He can continue doing his own thing. You can think of it as, entering somebody's office while they're on a meeting and delivering them a mail, right? Without disturbing them. That's the put. Or picking something up from their home while they're still working in a teleconference, right? Without disturbing them. So those are one-sided operations potentially. But how do you do that? Well, you have to make some of your memory accessible to other processes. And that's this yellow thing that's highlighted here. And in many programming languages, you have to explicitly say what memory you're making accessible to others. And there is a limit, right? You can't do it more than your memory, and you want to leave something for your private memory. But I don't think there's a hard constant. And those things globally, everybody's remotely accessible memory, every process's remotely accessible memory, are globally called the global address space, because now anybody can address data that is sitting in that this aggregate space. Cool. I don't think this is the two-sided memory model, communication model. Send, somebody posts to receive, data moves, and so on. And in the one-sided, the processor sends, the other processor is basically not doing anything. The other processor doesn't have to get this data to its buffers, doesn't even need to be acknowledging this thing, depending on which one-sided communication you're using, and this data directly goes to the memory segment. And why is this important? Now imagine that process one, even if your computation is seemingly load balanced on paper, can see some delay due to an operating system interrupt or some other external thing. And this delay can be also ingrained in your computation, meaning your computation might be inherently load imbalanced in an unpredictable way. So when you're doing two-sided communication, you're trying to send the data and your recipient, the recipient of the data is delayed, you are also delayed, even though you don't need to be, because in one-sided, you can just directly put data to that process's memory, even if that process didn't actually come to the exact code line you anticipated it to come, and you can fetch data. So delays in process one doesn't affect the delays in process zero. That's fundamental benefit here. So let's see a little bit of syntax. Technically, you can upgrade any locally accessible memory that you have created. Let's say on the heap or even on the stack, I believe. Any memory can be upgraded. And MPI calls this remotely accessible memory as a window. So once a memory is declared remotely accessible, all processes in that window can read and write data to this memory location without synchronizing with the target. That's essentially the goal of one-sided communication. So you can create windows 3 different ways. This looks like 4, but the last one is grouped with the first 3 due to technical reasons. It's not exactly doing the same thing like the first 3, so ignore the last one for a minute. The first one is you have already allocated a buffer, like x equals malloc, and you want to upgrade that memory in some sense to be remotely accessible. And you can call MPI win create. And MPI, sorry, yes, MPI win allocate is a little different. That you don't have the memory. You want MPI to create the memory for you and make remotely accessible. Now, why would you want to use that? It actually, in many cases, it can be faster because MPI win create means that you have allocated this memory based on your local malloc implementation. And it might not be ideal for one-sided operations. So let's think about a case. This is a little deep dive into how this is implemented. There is, how do you address somebody else's memory? Is you don't know where their remote memory starts, right? Let's go back several more slides. Apologies. So you don't know what is the so-called the MPI bottom. MPI bottom basically is the address where the remotely accessible memory starts. And these address can be the same in each process or can be different. If it's the same in each process, that's called a symmetric heap because everybody's bottom address is the same. And now no process needs to keep track of the starting addresses of other memories because it's the same as its own starting address. So that makes life efficient. When I want to access line 5, I'm remotely saying from the bottom in process 2, I know that address is exactly +5 to my bottom because the heap is symmetric. Now, if I call MPI win allocate and ask MPI to give me address, if there is enough memory, it will likely create a symmetric heap so that it doesn't have to keep track of everybody's MPI bottoms. But when I create the memory and try to upgrade it with MPI win create, it's unlikely that that memory will be aligned. So those are those kind of reasons that make MPI allocate potentially faster, but understandably, it's not always feasible from a programming perspective. And there's the MPI create dynamic, which is, well, it's like MPI create, but you haven't allocated the buffer. You'll just do it later. And this way you can dynamically add and remove buffers from the window. Comes in handy because you just MPI win create once and keep detaching and attaching it later. Syntax, not much to describe here. Then you will have to just follow the spec instructions when you're using. Just know that only the data exposed in a window can be accessed with these operations and nothing outside. It's just base pointer, displacement units, pure syntax here. Here's how to do it in code. You want to create collectively memory that is of size, let me see. The first element is the size of the local data. So everybody is creating 1,000 integers and making it locally accessible, so globally accessible to every other process. So if you have P processes, you have P times 1,000 integers globally available to everybody. And then you can basically access this. Create dynamic. We described this, how this is done is just, again, syntactic sugar. You can read about this, but here's an example. You can create the memory up at the beginning without attaching anything yet. Then later somewhere, you can create local memory with malloc and attach that to the window you globally allocated at the top. And now that memory becomes accessible from all processors. Good. Now, we just described how to make the memory accessible to other processors. We haven't described how to access the data. And for that, we have these operations, puts and gets and accumulates. And we also have atomic operations called compare and swap and fetch and op. These are the equivalents of local compare and swap and fetch and op that is usually available as hardware instructions in modern CPUs. These are the network equivalents of them. And they're usually also compiled down to the hardware, because a lot of the network interface cards that allow you to do remote memory access actually have ability to do atomic operations, at least on integer variables. Floating point is tricky and likely not supported yet, but we might get there depending on the hardware needs. So put and get are fairly simple from the name. You are moving data from the origin to the target with put. And you're just putting some data in somebody else's remotely accessible memory. This is a single trip. So this is slightly important detail, because people are usually surprised when they see get taking longer than put. Well, the reason get takes longer than put, especially for small messages, is because it's twice the latency. Get means, as the origin process, I have to make a round trip to the target process and fetch the data. But that's all there is. Still, in both cases, the target process is unlikely to be disturbed. Now, there is this finally the epoch concept of when you can access the data. And the reason epochs exists is simply convenience, actually, and correctness. If you said the data is accessible remotely to anybody at any time throughout the computation, then you are in some sort of a trouble, because how are you going to enforce that the ordering of the operations? Well, you can go back to MPI barriers and enforce synchronization, but that defeats the whole purpose of using one-sided operations, which was to decouple data movement from synchronization. So if you're just creating one big access point, that's so-called epoch, and allow everybody to access everybody else's data, then you just need to insert a lot of synchronization, explicit synchronization calls. Epochs kind of get around this problem. You say, during this period of access or exposure, you can access my window. And after the epoch is over, you cannot access it anymore. So this is, in some sense, allows implicit synchronization. Okay, this is the remote memory access way of synchronizing. Important details about ordering operations. There's the rules we have used in shared memory programming do apply in this case, because it's actually fairly a right way to think about remote memory access and one-sided operations is thinking of them as generalizations of multi-threading, except in distributed memory. If you have a data race that is defined in the multi-threading class, which means there's two processes, two threads accessing the same data, and one of them is doing a write, that's a data race. It will still be the same in the one-sided operation land. If there's concurrent puts to the same location, that's the result is undefined, just like it would be in a multi-threaded, except now you're using MPI processes. If you are doing one get, which is a read with puts and accumulates, the result is also undefined. So that's another data race you should avoid and can be garbage. So without the explicit synchronization, the concurrent read and writes are mostly garbage, except for the accumulate. Now, accumulate is a slightly more advanced one-sided operation that allows you to do concurrent accumulates to the same location. And there is a definition of it. And you can read about this. If you can actually call accumulates with a replace, and one of them will succeed, and you won't get garbage. You might not know which one will succeed because two processes are calling accumulate at the same time. And you don't know which one will get there first, but you can at least be sure that you're not going to get garbage. And if the accumulates are coming from the same process, then they're ordered by default. So accumulate gives you a little bit more, guarantees than uncontrolled gets and puts. And finally, there is this synchronization routines. There is an active target mode and a passive target mode. I actually, frankly, never really understood the active target mode, because that requires the target processor to post some an access epoch and wait for it, which to me defeats some purpose of one-sided operations. And the passive target mode is those things happen on the processor that is accessing the memory. So the process that is getting or putting will so-called lock and unlock the memory it's accessing remotely. And it will never require a single line of code to be written at the target. So that's the passive target mode that I like, and it looks true one-sided operations. But I admit that there's uses of active target mode as well. So know those exist. And the syntax is just like that. It's the lock and unlock is misnomers, so don't get caught up on them. You're not really locking memory in the same definition that you would use for the locks we use in MPI, OpenMP. And you can define different lock types. And shared lock means you're actually not really locking, because other processes can access that. Exclusive lock actually means something like the real lock in OpenMP or pthreads, because at that point, then no other process can access that area, that window. And that's, folks, is all there is that I wanted to talk about, and which is at the end of our lecture. So thank you for listening. We haven't covered certain things like I/O. You can do fast MPI I/O. That's really actually efficient for many cases. If you're interested in fast I/O, I would recommend you read about MPI I/O. It works in many cases. Now, task creation, dynamic task creation and destruction are good ideas, but MPI never got around implementing them efficiently. So I would recommend staying away from that, and don't get too encouraged just because you read that it exists in the spec. The implementations are not robust for that. And that's all. Thank you very much. I'm gonna stop.